Hello, everybody. This lecture has been designed to focus on problems on beta and gamma functions. In an earlier lecture, we have enunciated the beta gamma functions, defined the two integrals, and also given some important and basic properties. Now we will see how those properties and formulas can be applied to evaluate certain special types of integrals. So the first problem which I will put up on the board is something like the following. We can say this is, let's say, question 1. Show how to evaluate an integral of the form zero to pi by 2 sine to the power of px cos to the power of q x dx. Obviously, in terms of the beta stroke gamma functions. So that is the problem. Show how to evaluate an integral of the form 0 to pi by 2 sine x raised to the power of p cos x raised to the power of q, and express the result in terms of beta gamma functions. Now, to do this, we'll have to invoke one formula which we stated when we were doing the lecture on properties of beta and gamma functions. I will put that down first. We have seen, I'll write that as we know. Beta mn can be written as 2 times integral 0 to pi by 2 sine 2m minus 1 theta cos, okay, we are writing x, so we just put x, no problem, cos 2n minus 1 x dx. This we have given as a property. In fact, we have proved this result starting from the basic definition of beta mn. We had proved this in the earlier lecture, in one earlier lecture. So we are going to make straight utilization of this property and see how we can evaluate an integral of this form. Well, there is nothing much to be done here except that we put 2m minus 1 as p and 2n minus 1 as q. So if we do that, if we say let 2m minus 1 is equal to p and 2n minus 1 is equal to q, then evidently we can see that m is p plus 1 by 2 and n is q plus 1 by 2. So if we substitute these values in this result, we will get beta p plus 1 by 2 comma q plus 1 by 2 is twice the integral from 0 to pi by 2 sine to the power of px and cos to the power of qx. So this little transformation allows us to put up something like the following on the board, and that we'll do up. So taking this up here, we'll write this transform, so it will therefore imply that beta, for m we write p plus 1 by 2 For n we write q plus 1 by 2 is equal to twice square to the power of 3 is cos to the power of 6. So here we are, we've got this trigonometric integral pardon me, reduced to an integral in terms of algebraic terms. So this can be written as 0 to 1 t to the power of 5. We'll split this 1 minus 3t square plus 3t4 minus t6. Expanding 1 minus x to the power of 3. 1 minus 3x plus 3x square plus minus x cubed. Now this will be nothing but 0 to 1. Let's write t to the power of 5 minus 3t to the power of 7 plus 3t to the power of 9 minus t to the power of 11. This is to be integrated with respect to t. Now this will be t to the power of 6 over 6. So we just write 1 by 6. Looking at the limits to be 0 and 1, this is 1 by 6 minus 3 by 8 plus 3 by 10 minus 1 by 12. 1 by 12. Now we'll see if we can take an LCM. The LCM is of course 120. Nothing less than 120 will do. 60 is not good enough. 60 is good for 12, 10 and 6 but not for 8. So this becomes an LCM of 120. 6 goes 20 times minus 15 into 3, 45 plus 36, 12 times into 3 minus 10 times into 1. So we have 36 plus 20 is 56 minus 55 and that is 1 by 120. So we are squarely home with whatever result we got earlier. So this is one point to note, that we need not always rely on gamma beta functions to evaluate these forms of trigonometric integrals, sine to the power of p, cos to the power of q. But the gamma beta functions and the properties obviously provide a very good tool for evaluating such general integrals. The next problem we put up is rather a straightforward one. We will try to evaluate this. It will not take more than a single minute. Evaluate 0 to 1 x to the power of 5, say 1 minus x to the power of 4. This is absolutely straightforward because it fits into the category of an integral 0 to 1 x to the power of m minus 1, 1 minus x to the power of n minus 1 dx, and this is nothing but beta mn. So by comparison we can write, by comparing this with the definition for beta mn, the given I is equal to nothing but, this is 6 minus 1. So one should be very careful. It is not beta 5 4, but it is actually beta 6 5. I is beta 6, 5, that is gamma 6, gamma 5, gamma 6 plus 5, where we use the formula beta mn is gamma m, gamma n over gamma m plus n. So we see that as we get and encounter these problems, we have to constantly apply the formulas and the results learned so far. So now this gamma 6 is factorial 5, gamma 5 is factorial 4, and gamma 11 is factorial 10. We will continue the evaluation. This is factorial 5, factorial 4. This we will write as 10, 9, 8, 7, 6, and then factorial 5. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 is factorial 5. So we've knocked this off. Factorial 4 is actually 24, but okay, we can do 8. We'll get into this 3 times because factorial 4 is 24. These 3 can now knock off these 6, leave a 2, and we have in the bottom 14 and 90. So the result, the bottom line is 1 over 14 into 90. That is 1 over 1260. That's it. The numerical part is not important. The important part in these problems, these class of problems, is how to convert certain integrals into known standard integrals dependent on beta and gamma functions. That is the purpose of this exercise. These problems will bring out the various ways of reduction. We now take up another problem which I have written down on the board. This is the third in this series, maybe the fourth. Evaluate the integral from a to b, x minus a to the power of 4 and b minus x to the power of 5 with respect to x, where x is less than b and more than a. In other words, we have taken in this particular form that b is more than a. That's all right, that's not a problem. Now, we could have taken general indices m and n here, m here and n here, or p here and q here, but I thought I'll keep some integral values so that the process emerges in a simpler way. We can always do that. So that will be in terms of a, b, m and n, but here I have given specific values to m and n. M is 4 and n is 5. So we will see how to go about this. We take a little substitution. We say let x minus a be equal to z. So dx is equal to dz. No change on dx and dz, they are the same. This is a linear translation from one variable to another. Z is x minus a, so the differential in x and the differential of z are the same. That is what is the inner meaning of this. Now we'll have to change b minus x to the following. So b minus x is the second term. B minus x means b minus z plus a, which is b minus a minus z. So our friend b minus x will change to b minus a minus z. This will simply change to z. The limits will of course change. Now x minus a is z. In other words, when we substitute the lower value for x as a, z is 0, and when we substitute the upper value for x, it is b minus a. So the limits change to, we'll write z upper is b minus a and z lower is 0. So the integral will then reduce to, we'll rub out this part and put the reduced integral on top. In fact, we can use this space here also and write this as upper limit is b minus a, lower limit is 0, x minus a to the power of 4 is z to the power of 4, b minus x is b minus a minus z, so we put b minus a minus z to the power of 5, and dx and dz are the same. So this is the reduced integral. There is one more step for the reduction which we will do from here as we go up.